Welcome back, everyone, to another lesson of WebGL 2.0. Today's lesson, I'm going to forewarn you, this might be a long one because this one's going to be a fun one. Today, we're going to experiment with making procedurally generated trees. In our case, a low-poly tree because more complicated trees require more complications and triangulating and creating all the vertices. But a low-poly tree is within a realm of, I guess, my experience and probably your, capability and your capability. But overall, it looks pretty good. And like I said, it's procedurally generated. So if I refresh, tree looks completely different. Not too much different because there is not a lot of threshold of variations. But refresh again. And I guess the bottom, some more of the branches decide to go more toward the bottom instead of going up. And refresh again, and everything goes back to the top. And the trunk is less curvy. But like I said, it's procedurally generated, and I went about this in a slightly different way. When I was researching how to create trees and things like that, there's fractals. There's something called L systems. Those are very kind of complicated algorithms for the most part to generate. Overall, they're not very complicated, but the problem is that in a lot of the tutorials and documentation, everything's 2D. There's no one really showing you how to do it in a 3D form, which is what I really wanted to do. And the thing is, doing with 3D, you kind of have to build these 3D shapes. You got to create all the triangles. You got to have things connecting together. So since L systems and fractals and whatever other variations I read up on did not show how to do it in a 3D fashion, only in a 2D fashion. So I had to sit down and figure out my own way of doing a 3D tree. So the solution I went about is, instead of trying to be a mathematician that I'm not, go about it as a 3D modeler. So, I've used Blender before. So if I was going to do a 3D modeler, I would start off with a simple shape and start extruding, resizing, scaling, rotating, moving vertices around. That's what I would do as a 3D modeler. So I decided to go that route and program the steps of how a modeler would do it. So we're gonna learn how to do an extrude. We're gonna learn how to rotate vertices. We're gonna learn how to scale vertices correctly. We've done a lot of that mostly on the GPU end with our shaders. Now we're gonna have to write all the code ourselves to resize and move the vertices around instead of using a matrix. So this is what we're gonna do. This is fun. Let's start looking at some of the code. So we're going to first off is fix some of the core stuff before we start getting into the tree stuff. So in our fungi extent function, in our lathe, I found a bug. So when I was building the tree trunk, I noticed that my Y rotation was wrong. And the problem is that I wrote the equation incorrectly from this site. I guess in previous lessons, I was using the X and Z axis for rotation, so I never noticed that the Y was buggy. So now Y is good. So that's one bug fix. Next. In dynamic mesh, I'm adding a new parameter called tvert component. It's really the component length of our vertices. Before, our dynamic mesh always had it by default, which is three vertices per vertex component. Or I learned a new word too when I was reading all my math books the last 2 weeks. I forget what there was. Another words for the components, but I'll remember it during the video. So today I want to start coloring the vertices for debugging. So instead of having a default of 3, you push in a value. So in this case today, we're going to actually need 4 floats per vertice. So basically you just end up updating dynamic mesh with the new parameter. Like everything that's hard coded now, it's now dynamic. So it goes here. When we create the float array buffer, let's see, find next. I think that's it. It's just pretty much all the places that is hard coded. So yeah, just here and here. That's it, right here at the end. And that's it for this file. So if we go to core, let me scroll to the top, do a find. So let's see, what Funcle class is this? In our core, vector3, so we're going to be updating our vector3 function. A scalar. So a scalar, it is just taking the 3 components for our vector3 and then multiplying them by a scalar. So this way allows us to, in essence, scale this a vertice from its existing position. And I have scale reverse because I think there was a math equation that needed to apply, but the scale has to be backwards. So the way multiplication when dealing with floats, they can't be interchanged. Like with whole numbers, when you're not dealing with fractions or decimal points, 2 times 5 and 5 times 2 is the same. But when you're dealing with 1.2 times 0.5 does not equal 0.5 times 0.2 times 0.2. You get slightly different values because you got to deal with like in a way I would explain like dealing with percentages. 2% of 5 is different from 5% of 2, essentially. So that's why this exists only for the matter of multiplying the scalar backwards, because the equation was written in C++. So C++ you can just multiply a vector object. JavaScript doesn't allow us to program operators. An operator is basically plus division, multiplication, just those operations. Since we can't program those operations into our objects, I had to kind of do it this way to be able to perform that math equation properly on a vector3. So that's the reason why I'm doing this, because this makes no sense in vector math, or like for a vector object doing in reverse. But like I said, it's because of my limitations in JavaScript. If I was doing this in C++, I wouldn't have this function wouldn't exist, because I would just program the multiplication operator, and then I could just say s times vector1 instead of doing it this way. So this way I can say vector1 times this, or this times vector, and that one operator function will actually handle it in C++. I think C# also has programmable operators. So like I said, a lot of languages kind of has it. It's just JavaScript does not. So you're gonna have these weird functions like this, and from time to time when you want to deal with certain math equations. So I spent too much time on that. So let's see. Now we're going to our quaternions. We have our function called set axis angle. I'm actually getting pretty good at understanding how to use quaternions. So hopefully that will start reflecting on you guys as well. This function, all it is you pick an axis and then the angle in which to rotate that axis. And I noticed I have a lot of problems until I normalize it. So I put a little warning here that any axis you use in this equation needs to be normalized. That's the only limitation. Else things just don't rotate correctly. I could, in essence, in this function, when you throw in an axis, that I normalize it automatically. But the thing is, sometimes I already have the things already normalized. So if I normalize it twice, I'm just wasting CPU time. So that's why I'm not normalizing it in here, because sometimes I do need to normalize the vector beforehand to do something else. So that's why there's a little warning when every time you use set axis angle for any kind of quaternion, depending on the language or the framework you're using, always check to see if it already normalizes it for you or you need to normalize it yourself before you apply it to this type of function. The next thing is copy. Very simple. It just makes a copy. It copies one quaternion to another. Fine. Next. This is probably the equation I was talking about that I needed that that thing. Is it here? Yeah, probably like here. I got to multiply 2f dot. Well, actually, no, dot doesn't make a vector. Oh, there it is. This is the reason why that scalar reverse exists, because I need to multiply the scalar times the cross product, and the cross product is a vector, vector 3. So rotate vec 3 is that it takes the existing quaternion, and you can pass in a vector, and you can rotate that vector. In previous lessons, we had to create a matrix 3 rotation, a rotation matrix basically, because it's a 3 by 3 matrix. And then when we create that matrix from a quaternion, I believe, then we didn't have to multiply our vectors. This way, I found a nice equation from Stack Exchange, and some guy posted it. Sadly, he posted the C++ version, so it took me a bit to translate it into JavaScript. So I got it working, and works pretty well, and it's a great way to just rotate vectors with quaternions. Since we're using quaternions, it saves us a step from creating a matrix, then multiplying a matrix. The only thing is we're doing a bunch of we're doing a lot of dot products and cross products, and then a lot of scalar rotations, and eventually we kind of just add everything up. I don't understand how this equation works since I don't know quaternions, but like I said, here's the original equation that does the job, and this is the JavaScript version of this C++ equation. So that's a great function. I love that. It took me a long time to find. I've been spending months trying to find a good quaternion vector rotation function. So I'm happy I found one that works really well. So thanks to the person who wrote that. I probably should give him credit, because like I said, I've been looking for months for an equation like that. So just to be nice and cool and give credit where credit's due, here it is. I guess they put the name at the end. Laurent, I'm sorry, I can't pronounce your name if you're seeing this video, but I want to say thank you, that this is a great equation. It works really well, and I love it. So credits to you. I'm all about giving credits to where it's due, because like I said, this helped me out a lot. So I just want to show you I'm not the brains behind the operation. I would say the old phrase, I stand on the shoulder of giants. Everything I know is based on the knowledge that people share online. And just like me, I'm sharing it back to you. It's just, you're now on my shoulders that I'm standing on a giant. So there you go. So that's rotation. What else we got? Okay, I got a bug in look rotation in quaternions. The only issue was the S was caps. So I guess when I was doing look rotation stuff, it was buggy for certain instances, and that's when I noticed that the S was capitalized. So it was screwed everything up. These end up creating not a number values for the thing. So that's that. Next. And I guess the last quaternion function I added is lerp. So we can lerp between one quaternion to another. And if you don't know what a lerp is not interpretation, interpolation. It's just, and this is like a linear lerp. So instead of like a slurp, which is more circular, it's kind of like a curve. Linear, linear is kind of like a straight transition from one value to another, and a spherical one has like a curve, so it might be slower or faster depending where you are on the curve. So I don't have slurp because I don't need it right now. Down the line, I might end up adding slurp. Where linears are kind of like a constant. Sometimes you kind of want that variant of speed. So kind of like if something like slows down at the end, kind of like an easing type of function. So that's what slurp is. It's kind of like lerp, but with a slight easing into it, or it kind of just rotates in a, like I said, in an angular, in a curvy way. So yeah. So lerp, it's going from one value to another, the transition in between, and you use time, so it's between 0 and 1. Very useful function. What else is next? That's it for core. Now we're going to primitives. I think only thing I did was bug fixes. So I know in a couple of lessons ago we did a polar sphere, and when I was triangulating things, I had something turned off. So this way I was able to see both sides of the triangles, not realizing that I was triangulating the polar sphere backwards. Oh man, what the hell? Now I'm mad. What feature is that I turned off? Culling. Sorry. Culling. So when I had culling turned off, it would work fine. But then in this lesson, I turned it on, and the spheres kept doing this weird thing, and that's when I realized that I was doing it backwards. So I changed the for loop, where I was building the curve from top to bottom, like from North Pole to South Pole. What I'm doing now is going backwards. I'm going from South Pole to North Pole. And just going in a different direction allows me to use triangle strips the way we had it, that works with everything else, to triangulate the sphere with counterclockwise to show that the face is forward. So quick, simple fix. Like I said, I would have noticed the issue until I turned on culling. So I guess when I was doing the spheres, I had culling turned off, and that's why this bug got through. So that fixes, I think that. And Triangle Strips has a new setting, so I just put false for it. I think that's it for that. So those are all the changes to our core fungi, right? So now we're gonna finally build the tree. I'm sorry, I'm sure you're gonna hurry to get into the tree. The last thing I have is something called chi, and we're gonna go this little by little as we build the tree, because there's a lot of code here, and it only makes sense in context to what we're writing. So I'll come back here, and the reason why I call it chi, because a lot of this is built off of I would probably call it not the best way, not the best approach, because the data structure is just a flat array of floats to build up the vertices, and I need to build up faces and everything else. So the data structure is kind of complicated in the sense that it's too simple. I guess ideally, like a smart way of doing it, maybe we create like how 3GS does it, where they kind of have a geometric object, and then in there you have your vertices and your faces and your lines or whatever. And this way you can define everything in pieces, and then allows you to then build functions that are meant for faces, or meant for lines, or meant for vertices in general. Since, like I said, since everything is a flat array, I need to treat it as a flat array. So everything I'm doing here is really kind of a prototypey way to do it, and then at some point this should be refactored in a more structured way, so these things can then be brought into the core. So that's why they're not part of core; they're just part of chi instead, a different namespace. I couldn't come up with anything, since all this is meant for King's Kai's planet that I'm trying to build. I'm just calling it chi. So I want to explain why things are the way they are. Like, this basically is just temporary until at some point I refactor everything, and in a more intelligent way. Most often, you always have to prototype something in a very sloppy way, and then once you have the broad picture in front of you, then you can kind of like poke holes and restructure everything. So that's kind of how I have a habit of programming: prototype and then refactor, and then optimize while you're refactoring. I try to do and if you know how to optimize, do it beforehand. Save yourself some time. But like I said, sloppy, then you clean up. So we'll come back to this back and forth between here and tree proto. All right. So we got our two class files that we're going to bring importing: archaic Java and our Perlin noise. We've used the Perlin noise that I found online. We're going to do a little bit of Perlin noise just for fun. Calling is true. Triangle strips. All right. Now, one thing I'm going to do is in our vertex shader for which one is one? Just the DOM shader one, the default. I fixed up this if statement because I want to color all the vertices for debugging. So, like, this is a great way to kind of, if you're dealing with I'm trying to think. If you're dealing with vertices, sometimes coloring them, because I'm doing a lot of rotating, scaling, and a bunch of math equations on it. Coloring it makes it easier to tell where something is. If I program something, and I expect the vertices to be in a certain position, and they're not, I know something's wrong. So coloring it, each vertice a different color, helps debugging. So that's that. So here we are. We're going to build a dynamic mesh, and here's our new property because it's 4 components because I want to color the vertice. Using our DOM shader, the one I just showed you, that we quickly modify so we can color each vertice. Our draw mode is points, and this is our data points. So our data points are to build a square. And we're starting at the top left corner. And I think we're building this backwards or counterclockwise. Let's see, negative up, negative down. Yeah, counterclockwise. So this is built in a counterclockwise fashion. So this way we can triangulate things easier. And we pass in our vertices to create tree, which really doesn't do anything yet because I have a lot of things commented out. And we just update our model and we push it to the scene and we render. So just this stuff alone, I want you guys to see what we have. And this is what you should see. So basically building the square from the red to green to blue to gray, and I colored it in an order so this way so I can keep track of the order, because like RGB, and then gray's last because we ran out of colors. So so that's what we're doing first. Here is our starting point, and instead of using a circle or an octagon or any other odd shape, I pick squares because they're easy to triangulate. I'm cheating. That's the only reason why I'm doing this way. Doing any other shape is more complicated and requires a lot more code to triangulate and everything else. So that's why I kind of made it a LowPoly tree, and this makes it easier to. I guess it makes it a lot easier for you to learn the ideas of doing all this work anyway as a square. So we're doing everything as squares. All right, so now that we see our square being rendered, now let's go into our tree. So we got our create tree, our create tree function. So let's start at the top. So we pass in our model, and we're going to save references to our vertex array data and our index array data. Like, don't forget, these are just flat float arrays. That's all they are. Step is how many times we want to extrude. Make hole is determine when to make a hole in our mesh, because while we're building our mesh, I want to poke holes into it. And those holes will then be extruded even further and actually creates our branches. So that's what make hole means. Index list, we're going to keep a list of our index. So this way we can, basically this, like I said, if we had a geometry class, this would be faces. But this is, we're going to keep track of all our squares that we're drawing. Or quads. The real word is quad. And index last is just the last array of indexed for our last quad. And branches, we keep an array of quads to create our branches, our starting point. Got some variables, random y, random x, and scale. We're just going to loop through how many times you want to extrude our our quad. And as soon as we extrude, we save it to the last bit. So let's just uncomment this line of code. So we're going to pass in the last the last face or the last quad that we extruded, which the last one is by default the starting one. So we pass in the index of all the vertices that we want to extrude, and then we give it our v data because it's going to append new vertices onto our data array, and we're going to tell it which direction to extrude our vertices. So now we're going to go to chi extrude. So if we go to chi extrude, let's see. Now we need to calculate, like this is really kind of the reasons why I said that it's kind of a masochistic way of just doing everything as flat arrays. We're going to have to calculate the index. And the index is the length of our vertices divided by the component length, which I have by default set as 4 because we have 4 components per vertice because we're coloring each vertice. So like I said, this complicates things a little bit, but keep in mind that that's what we're doing. I'm trying to loop through. Am I even using this? Oh, okay. All right. This is what I'm doing here is basically getting the last index of in the array. So this is what I'm doing. So I'm going to grab whatever this is or whatever index we're doing, and then the last index in the array is kind of where we're going to start off. So we're going to say this, that, that, and that. Yes, because we're going to add 4, and then we're going to save 4 into our index. So yeah, so like this basically defines our face, and this just defines our vertices. So we're going to loop through every vertice in our face. We're going to calculate its point in the array. So it's index times component length. And then we just take that position and multiply it by the direction. And since I put 0.70, we're only going to move it in the y direction. And then we're also copying in our color. And that's pretty much all you do in extrude is you copy the vertices and then you move them. Very simple. And so if I click save, I go back, and there is our single thing, or single whatchamacallit, our single quad now extruded 7 times going in one direction. So ideally you can go any direction. Like I said, I built it this way so you can kind of pick any direction you want to extrude it. All right, so the next thing we should do is now let's start triangulating everything. So we're going to do a couple of small things. So we're going to take all those vertice points and we're going to triangulate it. So this way we can actually see the actual faces. And to do that, we're going to need to convert. We're going to start drawing everything as triangles again. and we're going to use our low poly material. So this way we can actually see it. So we're not going to use the color thing anymore. So now we're going to do the triangulation and go here and triangulate the wall. Now the way I triangulate the wall is that I get the previous quad and the current quad. And what is out? Out is the index. So we pass in the index array data. So this way we're kind of creating all the index, because the index is really all marks up all the faces. And we kind of denote an options like, is this the time to start making holes? And the value is if the hole equals -1 or it's not equal to P2. Basically, if P modulus 2 does not equal that, because the values I'm going to pass in is -1, 0, or 1. And based on 0 or 1 is basically, am I poking a hole in the wall either in the north-south sides or in the west-east sides? So this way kind of denotes if I'm cutting the holes one way or cutting the holes the other way, because I'm going to cut holes on both sides of the wall since it's a quad. It makes it easier to kind of just build branches that way. And then this is pretty much just the equation of how to triangulate two quads. And when I'm trying to triangulate two quads, I'm going to take the two squares and then just triangulate the quads that form when you rotate around it. So I'm not creating the top and bottom. I'm just creating the front, the left, the right, and the back, not the bottom or top faces. And it's just, like I said, it's kind of like trial and error. No, not really trial and error. It's just like if you draw everything out and then you kind of say, okay, this is really the positions everything needs to be at when you rotate around. I+1. This way, this one, this math equation just changed the position between, I think between 0 and 3. I think that's what it does, if I remember correctly. Because path per vert count is 4, and I'm adding 1 because I want to start further. I want to start at 1 instead of 0. So once we know the quad, basically this whole part right here is we're defining the quad of which part we're trying to triangulate. So once we have the quad, the points around the corner, let me, I guess, visually probably makes more sense. So the way I'm doing the triangle is I'm passing in the index of these bottom 4, then the new one I created. And then what I'm trying to do is define the 4 quads that basically makes that cube, because those 8 points together technically make a cube. So what we want to do is triangulate that face, this face, and then the back face. And that's all we're doing. We're just going around that cube and triangulating those faces. We're not doing the bottom or the top because we're extruding. So it's only the faces around that needs to be triangulated or turned into faces. So once we have those 4 points, like I said, we need to do it 4 times. And then there's the regular pattern, 0, 1, 2, 2, 3, 0. And that's the pattern we've been always using to triangulate a quad. And if we're not making a hole, we're triangulate it. If we are making a hole, we're going to save that quad back out to our branch out, because even though we're not triangulating this quad is going to be the starting point to extrude our branches. And that's what tri-wall does. So let's see if I refresh. And there is our tree. Now it sees like that because I have culling turned off or turned on. So I guess to make this look nicer, let's turn culling to false. Let's see the back of the faces. Refresh. There you go. So now you can see the square. Very nice. Very nice. So there's the beginning of our tree trunk. All right. So we're going back to tree. So what's the next thing we're going to do to it? Next thing I will. You know what? Let me show you how the hole is being poked first. So we're going to poke some holes. So this way you kind of see it a little bit. Refresh, and there you go. There's the holes. See, that's why I said if I do 0, I'm going to poke the holes, I guess, like north and south. And if I say 1, I'm going to poke the holes west and east. So there's the holes for our branches. And at the very end, I have a tri-quad. I don't know if I need to explain this one, but all it is you pass in a quad, and it just triangulates it. Very simple. It's like a single line of code. I pass in the index array, and then the output for the index, and it just does that pattern 0, 1, 2, 2, 3, 0. Very simple. So if I say save that, create the top cap, I refresh. There you go. Now you got the top cap on, because the top needs to be actually triangulated and covered. So this is what our tree branch or our tree trunk looks like now. Let's see what else. What else can we do? No. All right. So I want to comment this out for now. I don't want holes yet. Now, let's see. I want to start scaling, and because I want the bottom of the trunk to be thick, and I want the top to be thin. So I tried to do two different types of scaling. One is like a linear scale. It just keeps scaling linearly at 85, or like 15% shorter. Every time I extrude, I scale it down 15%. So if refresh, there you go. This is a linear way of scaling down. So, and it compounds, because remember we're extruding. So I make that one quad, I shrink it down. Then I make a copy of it and shrink it down. Make a copy of it and shrink it down. So it's every time you extrude, it gets smaller and smaller. Because, like I said, we're taking the previous vertices and duplicating them. So that's just a very simple scale. Oh, you know what? I probably should explain the scale function. That's right. Now we're going to scale. Scale is very simple to do. It is so I'm going to loop through each vertice in the quad, and I'm just going to multiply by a value. Just a simple scale. So if you, like I say, if you use anything between 0 and 1, you can scale it down. If you use anything above 1, you're scaling it up. So if I want to make it the things to be twice the size, I would then let's see. So let's try 2. If I want to make it bigger on one axis, I think that's the z-axis. Whoa, there you go. It just compoundly gets bigger and bigger by 2. So let me go and do that. Save. Go back to here. All right. So that's the first thing we're gonna do, because, like I said, tree it starts off really thick at the roots, and then gets thinner and thinner as it grows. So that's why I'm scaling it. But I didn't like it that being so linear. So I tried. I went to a graphic calculator online, and try to come up with a way to create a curve. And I remember reading in a math book that I think if I do something with pound, with a fraction, I can't remember it now. This was a lot of trial and error. But I created basically a curve. The idea of the curve is that I wanted to scale slower at the beginning and scale faster at the end. So that's the curve I wanted to create. And like I said, I used a graphic calculator to kind of figure it out. And doing pound sign is the is the magic, I guess. So using this math equation, refresh, kind of creates this. It's not the best curve, but like I said, it starts off really good at really slow. Like I wanted it to be big, but then at the when you start reading to the branch, it kind of slows down the actual scaling. Scaling is very, very slow. But basically, that's the curve that the graphic calculator I made when I was playing around with the numbers. So that's the curve. So like I said, if you go to a graphic calculator and just read a math book and like how numbers work, like I know if you do pound sign with like decimal points, I think it makes it easier to create a curve. If I remember correctly, because this was like 2 weeks ago when I did this, so I'm kind of forgetting how I did it. So there's the curve. So next, I'm going to start doing some rotations, because a tree is not very linear. So we're going to rotate, and we're going to rotate between a random number between 0 and 40. So every time we create a segment in our trunk, we're going to rotate it. And remember, just like scale, it's going to compound itself the further up the tree we go. So every rotation stays, and every next rotation that happens. So we might end up rotating back and forth, start creating these weird curves in our tree trunk. So now we're going to rotate by Y. So this is going to make our trees a little bit curvy. There you go. And see, since it's random, you don't know what you're going to get every time we refresh. So if I refresh a couple of times, sometimes it curves completely around, like this time. This time it just did a nice complete curve. Other times it kind of just goes back and forth. Like it's random, so you never know what you're going to get. And this is just rotating on the y-axis. So as it's going up, it's rotating. Now to make the tree trunk a little bit more curvy, because a tree doesn't go straight up in the air. A tree kind of curves. Like plants tend to grow toward the direction of light. So wherever the light is, that's where the tree kind of, every branch, every leaf, that's the direction they want to go at. So it's kind of random, essentially. Every tree shape is a little bit random. So we add a slight bit of rotation to on the x-axis. So as I'm rotating on the y-axis, now I'm going to rotate on the rotate on the y. Now I'm going to rotate on the x. This creates tilts. So this way, if a tree can end up curving all the way around, like in a circular fashion, but I'm not giving it the chance because I'm doing very low numbers, and I'm doing a random number between -10 and minus 10 and 10. So this way, I'm kind of basically tilting the quad back and forth, kind of like a seesaw action. So if I do a rotation on the x-axis as well, as long as with the y, refresh, now it starts to make a slightly more realistic tree. You know, like I said, it's as a tree grows, or as plants grow, they kind of grow in a direction of light. You know, the light's different in different times of the years. It might go in a different direction or whatever. The wind blows it. So I like how this one curves a little bit. It's more kind of a natural-ish feel to it. So this one's insane. This one is a crazy curvy tree. So if I just sit there and refresh a couple of times, you can kind of see our tree curves in a lot of different ways based on very slight rotations and the compound rotations. All right. So now that we got scale, we added our rotations, we got our tree curving up and down just right. Now we can put our holes back into the tree. Now we have our holes. Those are where the branches are going to start sprouting from. Oh, and I guess I didn't explain rotation. I'm sorry. I don't think I explained rotation either. So rotation. Just the simple rotation equations. And I believe this time around I got it right. So you just pass in your axis or your quad, the radians, and which axis you want to rotate by, X, Y, or Z, and the source is just vertex data array. So we're just going to loop through the quad. We're going to make a copy of our x. We're going to follow whatever math equation for that specific rotation, and then we save our values back in. So that's to say, we're just going into the array, getting the data out, changing it, and then putting it back into the array, and that quad is nicely rotated and around just fine. What else we got here? So that's rotation. It's not that it's kind of self-explanatory. I think we had it in core somewhere else. Like I duplicated it, but I needed it to work for the flat structure. That's the reason why it's duplicated. So that's rotation. Now we're gonna do our branches. So let's just save and see what happens. Now the idea is that we're going to, when we create a branch, you're going to take the starting points. Let me probably say. Remember, every time we do a tri-wall, we pass in our branches array. And if we're making a hole, instead of triangulating that quad, we save that quad indices into our branches. So at the end, we have like a list of branches. So technically, you can make a lot of branches, and it will use those as starting points for extruding. So for right now, I just set it up because I only need 4. I just want 4 branches. But like I said, this is kind of a starting point for you guys to learn. It's kind of just how about doing it. At this point, you can take this further and add more branches or do other things. It's just kind of a learning experience. So we're going to pass in our branches, our values. So this is like the starting. So we're going to loop through, and for every starting point, we call our branch function, and we're going to save e-points. And e-points is the endpoints of the branch. So when the branch is done being created, I want to know the endpoints. So this way I can add the bushes or the leaves or whatever you want to call them. So when we're, like I said, so when we're creating our trunk, we're saving the starting points of our branches. And when we're creating our branches, we're saving the starting points for our bush, trees, things. So if I refresh, as you can see, it follows the same idea. It just takes the vertices and extrudes them. And it just extrudes them in the direction that the original hole was. So if the hole was in a certain direction, it goes in that direction. So let's look at branches. And so quite a bit of math in this one. So the first thing we're going to do is we're going to get the quad cross product. So we want the cross product of the quad, and this is not the best naming for it because what I am doing, quad cross product. So I pass in the quad, and why the trying to remember what is the cross product is the parallel. Trying to think images. See, I don't have. I'm not even prepared for this. Images.google.com. Let me see. How do I explain this? 3-axis. I want an image. All right. Yeah, this is exactly what I want. Okay, a cross product. In case you guys don't know, it's kind of useful in to help determine direction. So the idea is you're going to pass in 2 vectors, right? It doesn't matter what the angle is, really, as long as there's 2 vectors. And when you follow the equation to create a cross product, it creates another vector that is, I guess, 90 degrees of both. So if this is like 20 degrees apart, like right now it's 90, but just imagine if they're just 20 degrees apart. The cross product is 90 degrees of these 2 points. So this is the cross product. This will always be 90 degrees. Right? So what I'm doing, that's why I say quad cross product. Let me see if I can find a nice image. Not really. I'm horrible. I'm sorry. So let's look at this image then. So we have our quad, right? So what I want to do is find the direction of where I want to extrude. Because remember, when we're building the trunk, we're extruding straight up. Very simple. But now we're creating a branch. I don't know which direction to go, because the rotation could be different. Its position could be slightly, because now we're doing all those rotations and scalings. Everything is topsy-turvy. So I need to figure out what is the forward direction of our quad. So like I said, the cross product is the 90 degree of a specific angle of two vectors. So I'm going to take the top corner of our quad, determine that vector from this point to that point, and then I'm going to determine the vector from this point to that point. And then when I do the cross product, it will give me 90 degrees of that point straight out, basically kind of like that blue line. That cross product is very close to the proximity, or it's very close to the direction that I really want to go in. It's not perfect because the vertices have been twisted up a little bit, but it's almost perfect. And since it's okay, it doesn't need to be perfect. It needs to be close to the direction that we want to go. Because remember that we're not trying to make perfect looking trees. These should look a little random. Should be a little off. So it's okay in this instance. If the quad was perfectly like aligned, like all the points were perfectly aligned at a specific axis, then that cross product will always be correct. But like I said, since we're doing so many twistings of the vertices, it's not exact, but it's a very close forward direction. So that's what I'm doing with that function. I'm basically taking just this corner of the quad and getting the cross product at that center point, so I can find the direction to extrude. So that's what we're doing. So figure out the direction we're doing. So, and I just normalize it coming out. So that's all this does is really just gets the vertice information. This, I create the vector that goes in one direction and the other direction using that corner, the top left corner, as the center point. And then CP is basically our cross product vector. Now, if we're going to extrude the first time, I want to go up a little bit. I want to go up in a different direction. So let's see. Okay. So now we're gonna do some more Quintorian fun here. Let's see. So, like I said, for the exact same reason, well, like I said, when we're doing the first one, instead of having the extruding going straight where it's going, I want to tilt it up a little bit, because a tree goes up when a tree branch grows. Like as you see an example, it's actually kind of going up and then going down. But I want to go up and kind of keep it kind of going up a little bit. So to do that, we need to determine its rotation axis, and the rotation axis is similar. So if we have our quad, this point to this point, if I create a vector from point 0 to point 3 of our quad, I can actually and then normalize it. That creates an axis. And that axis, in a sense, essentially, you can say this is the x-axis of the quad. So by doing that, dot product. So what I'm doing with the dot product is I'm getting the current angle, and I'm just gonna kind of add to that angle over here. So whatever angle it is, I'm kind of trying to tilt the angle up a little bit. Even though I'm going negative, that's how it works. You do negative, and I kind of point it up a little bit. And this part, I'm actually just creating that direction vector that I said between 0.0 and 0.3. That creates my axis. I'm basically creating the x-axis based on its current position in the 3D world, which has like a values in x, y, z that are different. So it's not like a 1, 0, 0 value. It's going to be like a bunch of real numbers. So once I have the axis of rotation and I know what my angle is, because dot product gives you basically an angle. If you use I use the up direction and the cross product, and that determines the angle that I'm currently pointing at. And so I set that axis, and like I said, I changed the angle just a slightly bit, and then I use rotate vec 3 to rotate the cross product. So like I said, the cross product is the forward direction. So what I'm doing is taking the forward direction and rotating it up just a smidge. And that's what all this is for. It's just that up tilt. This is, oops. Like you see, everything is going down because that is just the byproduct of everything. But that tilt up is that if statement. It's the thing that's pushing it up a little bit. That first segment is where the up is going. Because it goes up, and then after that if statement, it goes in whatever direction it's going, and it's straight down. So it's pointing in that direction. That's the cross product. It's going to go straight in that direction. So it's that if statement that creates that little upward bend. So, and then we extrude, just like we normally do, and we create a wall, and then we get the center point of the quad at the very end. Like the last quad that we generate, we get the center point. And the center point is very simple. It's basically the average. You kind of add up all the x and y and z components, and then you just average it out. And that actually creates the center of your quad. Very simple. Oh, that's right, I can stay here. So now we're going to start doing some variations. We're going to, like again, now we're going to, let's scale it. Or should we rotate it? What do we want to do first? Maybe we start rotating it, I guess. So rotate center. So let's see what rotate center does again. So rotate center. Trying to remember because I don't have a lot of rotation. So Q I marked them as a quaternion. So I'm using a quaternion to rotate. And rotate center. Oh, okay. The rotate center, I don't remember. It brings everything into the origin, because if you do a rotation where you're really far away from the origin, it has a big rotation. So if you just want to rotate the quad itself, you kind of have to bring it back into origin, rotate it, and then turn it back to the place it originally was. Translate it back. So that's really the cinch of it, what I'm doing. That's why I'm doing rotate center, because like I said, I need to bring everything back to origin. And I'm just rotating by rad. Is there a certain direction? V1. Oh, I'm just calculating its current axis again. For what we did with the if statement, that's what I'm basically redoing that again, what happens in the if statement, but slightly differently. So I'm basically taking the 0 and 1 point and then creating the vector and using that as its rotation axis. Basically, we're kind of trying to determine the x-axis that exists for that current quad, and then rotate it. And then we just apply it. We basically apply it, and then we kind of have to move everything. And C is like like I'm doing here, like this, let's see, where's C to calculate? That's the center point. And the center point of the quad can also be used as the distance away from the origin. So if once we know the center of a quad, it's like, well, that's how far away every single vertex is from the origin. So when we're getting its position, we subtract center, we do our rotation, and then we put our center back. So this, we're moving it back to where we found it. So that's what rotation center is. Because like I said, if you translate something and then rotate it, then you kind of make this big arc of rotation. But if you rotate something, it rotates itself, and then you move into position. So the order of operations depends on how the main object be rotated. So that's why I need to do all that moving first. So with that in place, let's see what it looks like now, our branch, when we start rotating from the center. So I'm starting trying to push everything to go in the up direction. So it's starting to look more like a tree branch. And the next thing we do is we're just going to scale center. And scale center, I think, follows the same rules as rotate center. Scale center. Yep, we have to bring everything back to origin, because if you scale not from the center, things go bad. So that's why I kind of have two different things, scale, and I think this scale doesn't even do the Z. No, it does. Based on the values you pass in. But so that's what I'm doing. I'm scaling everything, but I'm moving everything back to the origin. I do it in this instance. I can do it all in one nice equation. You subtract it, then I add the scale, and then I add it right back. It's quick and easy. So if I save that, now our tree branches should now start getting smaller. There you go. Now I kind of hate this part, but that's just the nature of the beast, really. But like I say, if you refresh, you'll see our tree branches and our trunk starts going in all these different directions. Very random, low poly tree. Now we're almost done. We got to basically, I guess I think my wife called it like a sleeping willow. I think that's what this type of tree might look like. If I had more branches, we would call it a sleeping willow. So that's branches. Now we're going down to the bushes. So now we're going to do the bushes. And I think I do that in trees. So this is the final part we're going to comment out. Like I said, at the end of every branch, we save the point at the end of the branch, or the point, the last quad, the center point of the last quad, and we use that as the starting point for our bush. So refresh, boom, and right now our bushes are going to start off as spheres. And if this is all you care about, then you're done. But I want these to look a little bit more realistic. So create bush. And I'm building the sphere differently than the last time. In primitives, I build the sphere as a path, and then I use lathe. I'm not doing it this time. This time I'm using, I guess, like polar coordinates to do it. I'm using like the longitude and latitude. So basically, I'm gonna loop through what are the degrees between north and south, and then the degrees around the sphere, and it's 2 for loops. So I'm gonna loop around first, and then I'm going to loop the north to south. And this is really all it really is to it. It's basically how many horizontal steps and how many vertical steps you want to take. So basically pi is half a circle. So how, you know, and like from north to south is half a circle. So I want to divide half a circle by steps minus 1. And then if I want to go 360 degrees, it's pi times 2. So 2 half circles, and how many times around I want to go. And that's the simple equation for it. And then basically I'm just incrementing. I'm going to start at pi because I want to start in a certain location, and then add our increment times, or our current increment times our actual increment value, adds to pi, and that creates our angle, or our angle around the planet. Basically, our, I think it's longitude or latitude. I forget. I keep forgetting which one is which. That's why I call it horizontal, because to me that makes more sense. I think that's the other name for it, azimuth and elevation. Elevation's up and down. Azimuth is around and around. And this is pretty much the equation for converting, I guess, like polar coordinates to x and y, z positions. And you'll see that I have x, y, z, but over here I have it marked x, z, y, because these are flipped. The equations are flipped on purpose because these equations was meant for z being in the up direction. OpenGL doesn't use z in the up direction. It uses y in the up direction. So I had to swap them out. So even though this is the equation for z, I'm putting that in the y position. So I commented that out. I commented in there just in case you see this equation somewhere. You'll notice that you have to make things backwards when you're dealing with OpenGL. So this what creates our circle, or sphere, I should say. And we triangulate, we add our mesh, we add our renderable, we move it into the position that we want it, the end of the branch, and then we kind of push our model into the scene. Ideally, the bushes should be either children of the trunk, or the really smart way to do this is, instead of creating separate models, you should somehow include it all in one mesh. So this way you can do instancing. So if you do instance of the tree, you can then create like a forest. Someone on Reddit asked me, can you create a forest since it's, yeah, it's like, yeah, you can. The way I'm doing it now makes it a little harder. But like I said, ideally, the smart way to do it, if you want to do instancing, create forest, is that instead of creating a model for the trunk, and then separate models for each bush, you should try to combine them all into one mesh. If once they're in single mesh, you can use instancing. So this way, basically, you create one model, and you set up an instance. And then an instance is basically just an array of matrices that kind of sets the rotation, position, and scale. And you can just create a huge array, like an array of 1,000 matrices, and you just push it to the GPU in that one mesh, and it'll create a forest for you. Maybe down the line, when I refactor everything, maybe I'll try building a forest this way. But for now, just mind you, if you want to build a forest, you need to kind of fix this up to kind of melt this all into one mesh. You can still build everything as separate meshes. Then at the end, have a function that combines all the meshes into one mesh. That's another approach you can do. If you just want to take the code that exists now and just add on to it, just like I said, make a function that takes all these meshes and combines all the indices and all the vertice data all together in one big go. So that's what we're doing. So let's start messing around with the circle. So one of the things I tried, let's just try random numbers. Like this is not the final product, but I wanted the spheres to be a little bit more random. So there you go. And this is what random does, really. Kind of makes a lot of points. I needed a better zoom out value. But for overall, it does a pretty good job. At this point, if you really want, you can just stop right here and you're kind of done-ish. But I wanted to play around with it. I wanted things to be a little bit more uniformed. So since I wanted things to be more uniformed, I decided to use Perlin noise. So these are just numbers that I kind of just trial and error, just to try to create something that makes sense or that looks kind of good. And this if statement is basically doing where I'm trying, since I'm building a sphere with polar coordinates, there's a north point, and then there is there's a north point and there's a south point. So I don't want to modify those points. I want the north and south point to always stay where they are. So that's what the if statement is doing. Basically, if it's a north and south point, it's just the default radius, which I have probably up here. Default radius. It's just, in the default radius is going to be a random number between 1 and 2. So each time you create a bush, you still have a slight different size of radius. So that the overall tree can be big or small between 1 and 0. Between 1 and 2. And then, like I said, just add Perlin noise, and it creates a radius, and then we use the radius to determine the x and y position of our points in our sphere. So right now you can kind of see everything's kind of just random, and if I do this, they still look a little bit random, but they're a little bit more orderly. They're less than, and the thing is, when you refresh, they always stay the same, because there's not really a lot of randomization when it comes to Perlin noise, because everything, even though it's random order, or it's organized order, as I would describe it. So, but to me, it makes it a little bit better than just random. But if you like random, just use random. It's one less, a lot less math equations you're dealing with. So the final thing I did was that I wanted to scale the x and z position. So I want to make the bushes wide, but not tall. So now when I refresh, now they're just wide. So I just made them wider. And that's pretty much it. That's our tree. The only thing you can do next, which I didn't bother, because this is good enough for me, add rotation. Just add a random rotation, maybe a random rotation and a random axis, and then you can just apply that to your model. Since we're building models out of them, so right here at this point you can just add a random rotation, add a random axis, because you have a quaternion, so you can just make a random number, make an array of 3 points or of vec3, and have a random x and y z value. Make sure that it's normalized, and then just create a random. So that creates a random axis, and then all you got to do is then make a random value between 0 and pi times 2. So this way, you do between 0 and 360-degree rotation. Unless you want always to guarantee rotation, then you do something like maybe something between maybe 100, maybe 10 to 360. Or actually not that 360 to maybe we'll do 1 to let's say 25 to 300. So this way you got a good rotation, and it's never going to be exactly the same, instead of just rotating something completely 360. But the axis is random too, if you make that random. So you have no clue what you're going to get out of it. You can make the radius a little bit more random. You can make it a lot smaller. You can do 0.5, I guess. 0.5. Let's see what it looks like. So it might make the bushes more variant. Refresh. It makes a little, you need more variation of size. That one's a lot smaller. That's really big. That's close to 2, and that's probably close to 0.5. Like I said, a lot of the numbers are kind of hard coded. You can kind of play with the numbers a lot throughout all the functions. Ideally, if you're going to do this, learn how this works, and then sit down and construct a proper, I wouldn't say a framework, but a set of functions to generate the tree for you. So that, how many branches to make, how long to make the branches randomly. Maybe you want to make one branch really small, maybe make the other branch really big. Add more randomizations, things like that. Because like I said, a lot of values are hard-coded. You can make these part of the function calls or like parameters of an object. So this way you can predefine all the settings of how to randomly create a tree. I'm not doing all that for you, like I said, because I just wanted you guys to learn a method of how to create a tree. And I guess this is pretty good, because like there's really no tutorials on how to do this in a 3D fashion that actually teaches you the vertices and everything else, and how to scale and build everything up. So I'm kind of hoping this tutorial really helps a lot of people out in getting into this, because there's a lot of good stuff out there. It's just a lot of it doesn't teach you in 3D. A lot of it is in 2D, which kind of stinks in a way. So I'm kind of hoping that this my little part in helping people build trees in 3D. So ideally you could probably take the same idea and then use L systems. L systems allow you to create more realistic trees. The branches go in all these different directions. It's like more random. It's a more complicated algorithm, but definitely look it up. There's some great videos online about that, the L systems, trees. So there's some cool examples of fractals. But fractals aren't very random; they're very organized. But if you're doing with like I like LowPoly. Like if you're a programmer and you don't have I say I have a design eye. I always say I'm an artist first, programmer second. So I don't have much of an issue. But if you're a programmer first, then an artist, I can't remember if I said it right the first time. I always say I'm an artist first, then a programmer. But if you're the opposite, you're a programmer, you're not very artistically inclined. LowPoly makes things easier. Like I said, it's just this tree is really just a bunch of squares. Quads. You might not even realize it, but that's what it is. It's just like first looking at it, it's just a bunch of quads that we extruded over and over again and added a bunch of random rotations and scalings and whatnot. And then you didn't probably realize that the bushes were really just spheres that we just meshed around the vertices around a bit. So yeah. So I'm kind of hoping this works out. I hope you guys like it. This is not the end of trees. Like I said, this is really a starting point for you guys to learn. There's more material out there. There's more complicated, better algorithms for this. Like I said, to me, this is the poor man's tree that I created. I guess this is originally a sketchpunk fungi tree from scratch. That's why it took so long to make this video, because it's not like I can learn a bunch of tutorials, learn really how to do it, and then make my own way of doing it. This one I actually had to make my own way from the very scratch. But I'm very happy with the results. I hope you like it. It'd be kind of great to see you guys make forests out of this. Like if you guys really take this to the next step, and that's some really random. That's a very unique tree. This is great for platforming. You jump onto this one, you jump on the other ones. Yeah, whatever. I don't know, but that tree is very random. I kind of like it though. I don't know. To me, it makes me think of platforming. Like you should jump on that tree. You got this one. This one's all ganged up. Like this is the runt. The runt of the litter is the one furthest away, and everyone's all together. I don't know. It's kind of funny. It's just kind of funny when you see it. Sometimes the trees look really bad, and sometimes they look pretty good. That bush is inside that bush. It's metaphor. I don't know. It's funny. This one looks like this one turned out pretty well. This one, yeah, not bad. I don't think I like it being down to 0.5. I prefer 1 to 2 because when it gets too small, it looks a little off. If it's like 1 to 2, and these would be bigger, this tree might look pretty good. But yeah, I don't know. This is great. I love this. This is fun. I just can't believe it. Like a year from now, or a year ago, I couldn't understand a single crap about this stuff. And then a year later, from scratch, I'm making trees from math. This is great. So like I said, this approach is an approach more inclined of like an artist. Like I said, I'm an artist first, programmer second. Even though I'm a better programmer than I am an artist, this is an approach of a 3D modeler. You start with some points or some faces, and you start extruding, and you're rotating, and you're pulling and pushing and messing things around. The only thing, instead of me using Blender, I just use math. I just use math. And I created the functions: scale, extrude, rotate, and all the other functions. And I use those as my tools to modify and manipulate the vertices. So hopefully now you guys know how to do this, and this can be a stepping stone to do a lot of other things. Maybe you guys have some really cool ideas. I would like to see what kind of cool ideas you have to take all this chi function that I put together, and what other things can you do other than just trees? I'm curious what you guys can do with just using 3D modeling techniques in a programming sense to build dynamic models. I'm pretty sure you probably can build like a city. In all honesty, a city pretty much consists of just a bunch of squares, and then you extrude it and then scale it up. Technically, you can do that too. Build cities, random cities, and do it in a grid kind of fashion, or whatever. I don't know what else you guys can do. I'm sure you can build dynamic houses. Like anything square is very easy to do. Anything that's square shaped is very easy. And even though you're not dealing with squares, you can still use spheres and whatever. Maybe you want to try using an octagon. You can probably use like a hexagon, has 6 sides, and then branch out as squares. So this way the tree trunk could be more circular, but then the branches are more squarish, like how they are now. Unless you want to figure out how to take a square and then kind of like subdivide it and then put it into, and then retriangulate a little bit. Like I said, it becomes more complicated when you use shapes more that are greater than a square. So that's why I cheated. That's why I said at the very beginning, I'm cheating by using a square, because when you're dealing with anything that's not a square and you want to cut a hole into your mesh to then use it to extrude, you can do that. Or you can cheat. Now, mind you can't cheat. You don't have to poke holes into your trunk. Let's say you can use a hexagon or whatever, and then pick a random point anywhere in the trunk and make sure that the branch starts inside the trunk and then it comes out. So even though you might actually have an extra set of vertices that are hidden inside the trunk that you can't see, you can do it that way. So you're not punching holes into it. You can just building branches in any direction. You can do it in that way. So but you might end up having a bunch of vertices that are useless, that's hidden away inside the trunk. They don't get rendered. If you're going to do that, I would say when you optimize it, you put all the branches in the beginning of your vertices array, and then the trunk goes last. Now, the reason why I'm saying that is because any vertice because if you use depth testing, like this is an optimization trick. If you're doing depth testing and the vertice, I'm trying to think. No, actually, no, it's the other way around. You should do the trunk first. So when the trunk renders and there's depth testing, the branches inside, even though the vertex shader will run, it's the fragment shader that will not run, because it'll see that those vertices are behind a depth test. So like if it was inside the vertex was inside the trunk, but the trunk was rendered first, the depth testing would say, well, this part of the tree trunk, this part of the tree branch lives behind the trunk. So even though I'm rendering the vertices to determine that, I'm not going to render the triangle with the fragment shader. So I said it wrong. The trunk should actually render first, and then the branches should render second. So this way, like I said, you can use optimization with depth testing to prevent the fragment shader from actually rendering. So you do waste time in the vertex shader, but you will not waste any time in the fragment shader by doing that. So those are just a little optimization tricks to help process things a little bit quicker, because you don't want to waste time. If you do it the other way, if you do branches first, then the trunk, then you wasted time rendering a bunch of triangles that are going to be then covered up by the trunk. So yeah, I made a mistake in my way of thinking. So trunk first, trees. But like I said, you don't have to cut holes. You can just randomly put trunks, and at that point you can use any shape you want. You can make very detailed circle shapes and extrude them, rotate them, and do a whole spiel. So you can still do that. I just wanted to do the cutting because I think I wanted to keep one complete mesh, and that to be a fun thing to teach you, because the other way is kind of cheating, and you can get away with it. The only reason why I didn't do it, also didn't do it that way, because if you're putting something inside the trunk, it might not render 100%. Like I wanted these really sharp edges when like I really wanted these like sharp edges to show up. So because I really wanted that low poly effect. So, but if you're doing highly detailed things, you really don't care about the low poly effect. So, so you might get away with it. So give it a shot. Like I said, it doesn't hurt to try. It's always fun to prototype because you always learn something new when you prototype. So there you go. There is your low poly tree procedurally generated. This is probably a very long video. I'm sorry, but I hope you learned and hope you had fun with this. I'm probably gonna have one more video after this, but the next video I'm just gonna do a bunch of things that really is just a rehash of everything we've done so far for the King's Kai milestone. So hopefully the next video would be the King's Kai's planet completely finished. So the next lesson probably be small things. I'll just probably gonna finish creating the material object, because I need the material object to work right. And then I need to build a couple of extra shapes, like the house, the shed, and then something else. There's something else on King's Kai's planet, but they're all the same thing. It's just lerping and extruding and shaping, things like that. So I'm not going to bother teaching any of that stuff because it's really all the same stuff that we've been doing. I'm just using different shapes to build different objects. So the next video you'll see will probably be me just really showing you how to complete the materials object, because I need the material, because the way the materials are set up, it's hard-coded and it's not dynamic to update the uniforms. So what I want to do is be able to color every object differently in with the low poly shader. Right now everything's hard coded. So next lesson is really gonna be taking our low poly shader and our materials and upgrading it so they're more dynamic. So this way we can add, so I can make the tree branch or the tree trunk brown, and I can make the leaves green using the same shader. Like right now everything's hard coded and everything's the same color. So but hopefully in the next lesson will be the end. It will be the completed version of a low poly King Kai's planet. So okay, we can't wait to see it. This is going to be fun, because after we're done with King Kai's planet, I'm going to go straight into bone animations and start dealing with that, because it would be great to load in models and then animate like humanoid bodies and stuff like that. So that's really the next milestone after I'm done with King Kai. So we're almost there. One more video and I'm going to start to go into more advanced and more fun stuff. So I guess I'll see you guys in the next lesson. I hope you learned a lot. I'm sorry for this video very long. Like and subscribe. Have any comments, whatever, questions, ask away. I'm also on Reddit. You'll see me there a lot on the WebGL forums. So if you have questions, you can call me there too. So see you guys in the next lesson.